Welcome back to Behind the Pages. When I first started building Noet, I really only had one goal. I wanted the world to feel believable. I knew there would always be readers who asked, could that actually happen? Does the science work? Would a planet like that even be possible? Instead of avoiding those questions, I decided to let them shape the world. So I started reading about exoplanets. I had no idea what kind of planet Noet would be. I was simply looking for inspiration grounded in real possibilities. As I looked through the planets astronomers considered the most promising candidates for habitability, I learned that many of them orbit red dwarf stars. Then I noticed another pattern. Many of these planets appeared to be denser and larger than Earth. I hadn't planned on that. It was simply another piece of information I had to work with. So I asked the next question. What does a denser planet actually mean? The answer was stronger gravity. Well, now I had a problem. Stronger gravity changes life. It tends to produce shorter, stockier organisms. I remember thinking, well, that isn't exactly the world I was imagining. So I kept researching. Eventually, my thoughts drifted back to visits to natural history museums. The dinosaurs. Instead of asking how stronger gravity would shrink life, I started asking whether other environmental conditions could allow life to become much larger. That question led me to somewhere completely unexpected. Temperature. How do planets maintain habitable temperatures? That took me down yet another rabbit hole. I already knew different forms of electromagnetic radiation affected the world in different ways. Microwaves heat our food. I had also been reading about directed energy technologies that use microwave radiation in entirely different ways, such as modern global telecommunications, navigation, remote sensing, lasers, and weaponry, which fascinated me because it showed how much energy these invisible wavelengths could carry. Around the same time, infrared therapy has been becoming increasingly popular with skin treatment, and ultraviolet light is also being used in medicine to treat certain skin conditions such as acne. I am also extremely pale, meaning I have a lot of experience with sunburns. So I already knew that different wavelengths of light interacted with matter in different ways. But there was still a problem. From everything I had been reading, a red dwarf star by itself didn't seem capable of providing enough energy to keep a planet comfortably habitable. So I started asking a different question. If the star isn't the only source of heat, where does the rest come from? That question led me to beneath the surface of the Earth. I learned that our planet isn't simply warmed by the sun. Earth is constantly releasing geothermal energy from its interior. Heat generated deep within the mantle and core slowly flows outward through the crust and eventually radiates into space. That completely changed how I thought about planetary climates. Instead of asking whether a red dwarf could do all the work, I started asking how much of the planet's warmth could come from the planet itself. That opened another door. If Noet had more active volcanism, if geothermal heat continually escaped through the crust, then the star and the planet could work together. The red dwarf didn't have to do everything on its own. That realization became another piece of the puzzle. With all of those separate pieces, gravity, temperature, atmospheres, habitability, they started connecting. I didn't build Noet by beginning with a vision and then looking for evidence. I built it by following one question after another. Every answer created a new problem. Every problem forced me to learn something new. And eventually those questions stopped feeling less like research as they finally became a world. People often ask whether Noet has stronger gravity. The answer is a little. Gravity isn't determined by the star. It's determined by the planet's mass and radius. Many rocky planets discovered around red dwarfs are Earth-sized or slightly larger. That gives them Earth-like gravity, sometimes slightly stronger. Higher gravity also helps a planet retain a thicker atmosphere, which becomes extremely important for sustaining clouds and redistributing heat. The atmosphere couldn't simply appear. It had to be constantly maintained. That's where geology entered the story. Volcanic outgassing continually releases water vapor, carbon dioxide, nitrogen, and other gases. Plate tectonics recycle greenhouse gases. Comets contribute to additional water. The atmosphere becomes a living system. Instead of a background scenery, the planet itself becomes the character. One consequence of a red dwarf's low temperature is that planets have to orbit much closer to receive enough energy for liquid water. Astronomers call this the habitable zone. Around a red dwarf, that zone sits far closer to the star than Earth's orbit around the sun. At first, that sounds like a great advantage. The planet is close enough to stay warm, but that proximity creates an entirely new problem. The star's gravity exerts enormous tidal forces on the planet. Over millions of years, those forces gradually slow the planet's rotation until one side always faces the star. Astronomers call this tidal locking. It is the same reason our moon always shows Earth the same face. The difference is that on a habitable exoplanet, an entire civilization would live on that locked world. So with a tidally locked planet, you have the permanent day side, the permanent night side, and between them, a narrow ring called the terminator zone. Without an atmosphere, the day side becomes hotter than 1,000 degrees Fahrenheit. The night side can fall below negative 148 degrees Fahrenheit. Neither can support life. Life exists between them. Therefore, the environments in Noet will literally shape each civilization. Once I understood that, I realized I wasn't simply designing a different planet. I was designing a completely different way of experiencing time. On Earth, we organize our lives around the sun. The sun rises, the sun sets. The seasons change as Earth's 23.5 degree axial tilt causes each hemisphere to lean toward or away from the sun throughout the year. That rhythm affects almost everything. Our calendars, our agriculture, our holidays, even our biology. A tidally locked planet doesn't have any of that. The same side always faces the star. The day side is always day. The night side is always night. The twilight zone never experiences a sunrise or sunset. At first, that seemed like a huge problem. How would anyone know what time it was? How would they recognize seasons? How would civilizations build calendars? That question ended up changing the entire planet. On Earth, the changing seasons are created by our planet's 23.5 degree axial tilt. A tidally locked planet around a red dwarf is different. The planet's tilt approaches 0 degrees, meaning its axis remains nearly upright, so the terminator stays parked over the same regions year after year. There are no northern summers, no southern winters, no seasonal march of sunlight across the globe. That meant I had to find another way for Noet to experience the passage of seasons. The answer wasn't the planet's rotation, it was its orbit. Not every planet travels around its star in a perfect circle. Some follow slightly oval or elliptical orbits. That means there are times when the planet is closer to the star. and times when it's further away. As the planet approaches the closest point, the entire world receives more energy. The permanent day side becomes hotter. Evaporation increases dramatically. Storm systems intensify. The cloud formation accelerates. Then, as the planet moves towards the furthest point from the star, the entire world cools together. Instead of the northern and southern seasons, the whole planet experiences what you might think of as a collective summer, followed by a collective winter. That was exactly the kind of seasonal rhythm I needed. Then I discovered something even stranger. Even though the planet is tidally locked, the star doesn't appear perfectly motionless. Because an elliptical orbit changes the planet's orbital speed, the star slowly rocks back and forth across the sky. Imagine standing in the same place every day. Instead of watching the sun rise and set, you watch the red dwarf slowly sway, almost like a pendulum of an enormous celestial clock. The cloud shield itself isn't fixed. It follows the hottest point beneath the star. So as the star slowly sways, the giant cloud system sways with it. Storms migrate, wind patterns change, moisture shifts across the terminator. Some regions experience strong storms, others become calmer. Some areas warm slightly, others cool. For civilizations living along the twilight zone, time isn't measured by sunlight, it's measured by weather. The movement of storms becomes the calendar. The rhythm of the wind becomes the seasons. The sky itself becomes a clock. That's when something clicked for me. I stopped thinking of Noet as a planet and I started thinking of it as a living organism. The day side continually breathes warm air upward. Clouds form. Heat is reflected back into space. Atmospheric currents carry warmth toward the night side. The night side cools. The air sinks, then flows back toward the light again. The entire planet is constantly breathing. Once I understood that, the weather wasn't just background scenery anymore. Then I wondered if I could also include a moon or two to further create time. I started reading about something called the Hill sphere. Every planet has a region where its own gravity dominates. Astronomers call this the Hill sphere. It's the zone where a planet can hold on to moons. On Earth, that region is enormous. But planets in the habitable zones of red dwarf stars orbit incredibly close to their stars. That changes everything. The star's gravity squeezes the planet's Hill sphere down to a much smaller region. Large moons become difficult to keep. Over long periods of time, they can be pulled away by the star's gravity or become gravitationally unstable. In other words, one of the most familiar sights in Earth's sky may never even exist at all. No moon. That discovery solved one problem, but immediately created another. On Earth, the moon has shaped our cultures for thousands of years. It influences tides, calendars, navigation, stories, religious festivals, even the way we measure months. Without a moon, how would people keep time? By this point, I had figured out how time may work. Without a rising and setting sun, I realized the civilizations of Noet would have to tell time differently. The same atmospheric circulation that could create predictable storm cycles also solved one of the biggest problems facing life around a red star. How do you keep one side of the planet from burning while the other side freezes? The answer turned out to be the atmosphere. Then I came across some climate models that suggest tidally locked planets may have their own built-in air conditioner. Because the star never moves from the day side, the hottest point on the planet also never moves. That constant heating creates an enormous engine. Surface water continually evaporates. Warm, moisture-rich air rises in powerful convection currents. As it rises, it cools and condenses into an enormous permanent cloud deck directly beneath the star. Those clouds become the planet's first line of defense. Instead of absorbing all of the incoming infrared radiation, they reflect a significant portion of it back into space. Astronomers call this the albedo. It's the same reason wearing a white shirt on a hot summer day feels cooler than wearing a black one. The white fabric reflects more incoming sunlight. The cloud deck does exactly the same thing for the planet. But the part that fascinated me the most was the feedback loop. The hotter the dayside becomes, the stronger the evaporation. The stronger the evaporation, the stronger the convection. The stronger the convection, the thicker the cloud deck. The thicker the cloud deck, the more radiation gets reflected back into space. In other words, the planet naturally turns up its own air conditioning. The climate begins regulating itself. That discovery completely changed Noet. I stopped imagining a planet with blue skies and scattered clouds. Instead, I imagined a world wrapped in enormous permanent cloud systems. Those clouds weren't just scenery anymore. They became one of the reasons life could exist at all. When I discovered that, I realized Noet didn't need an artificial explanation for surviving. Nature had already solved the problem. At this point, all these ideas finally started coming together. By themselves, gravity wasn't enough. Clouds weren't enough. A thick atmosphere wasn't enough. A red dwarf star wasn't enough. Each one solved one problem while creating another. But together, they started behaving like a complete planetary system. One discovery that really fascinated me was how infrared radiation reacts with clouds. At first, I assumed heavy cloud cover would simply block most of the star's energy, but that's not quite how it works. The shorter infrared wavelengths coming from the red dwarf star can penetrate much of the cloud layer and continue warming the surface. Then, something remarkable happens. As the ground warms, it radiates energy back upward as longer wavelength infrared. Those longer wavelengths don't escape nearly as easily. Instead, the cloud deck absorbs much of that outgoing heat and radiates a portion of it back toward the surface. In other words, the clouds do two jobs at the same time. They reflect enough incoming radiation to keep the dayside from overheating, but they also trap enough outgoing heat to keep the planet from freezing. They become both a sunshade and a blanket. The atmosphere wasn't simply weather anymore. It became an active part of the planet's climate control system. The dayside continuously feeds energy into the atmosphere. The cloud deck regulates how much reaches the surface. The atmosphere redistributes that warmth toward the twilight and night side. The cloud cover then helps prevent that heat from escaping too quickly back into space. Everything works together. The gravity helps the planet retain a thick atmosphere. Volcanic activity continually replenishes the atmosphere with gases. The atmosphere circulates heat around the globe. The cloud deck reflects excess radiation while trapping enough warmth to sustain life. The storm systems become the planet's clock, and the red dwarf provides a steady source of infrared energy that drives the entire system. By the end of all that research, I realized I wasn't building isolated pieces anymore. I was building an ecosystem. Every answer depended on another answer. Every scientific constraint became another opportunity to ask, if this is true, what else must also be true? That's how Noet slowly came into existence. Then came another amazing discovery. Red dwarfs don't produce light the way our sun does. Most of their energy is emitted as infrared radiation. They still produce visible light, but much less of it, and most of that light falls toward the red end of the spectrum. That meant the world wouldn't simply look different, light itself would behave differently. Infrared fascinated me because it isn't heat itself, it's electromagnetic radiation. When objects absorb that radiation, it becomes heat. It's the same principle behind thermal cameras, infrared heaters, even much of the warmth you feel from sunlight or a campfire. I started asking, what would evolution look like if most life developed beneath an infrared sky? That question actually brought me back to something I wondered about as a kid. I think most children eventually ask, do I see the same colors you do? It's a fascinating question. The green leaf we both point to is reflecting green wavelengths of light. That part is objective. But our eyes and brains are biological systems. Just as two people have different fingerprints, different taste buds, and different DNA, our visual systems aren't perfectly identical either. One person's green may lean slightly towards blue. Another person's green may lean slightly towards yellow. It's one reason people sometimes argue over the exact color of something while both genuinely believe they are seeing it correctly. Back in my 20s, before infrared photography was easy to find online, I tried solving the problem myself. I literally wrote out Roy G. Biv on a piece of paper. I started asking questions like, if our yellow sun gives us green forests, would a red sun give us orange forests? If our sky appears blue, would it become yellow instead? It was an interesting exercise, but I hated the results. Orange trees, yellow skies. It wasn't the world I imagined. Years later, technology caught up with my curiosity. Suddenly, I could study infrared photography and false color infrared imagery. Instead of relying entirely on imagination, I could actually see how landscapes changed when viewed through different wavelengths of light. The world I had been trying to imagine suddenly had visual references. Not because Noet literally looks like an infrared photograph, but because those images helped me break free from imagining every alien world through Earth's visual language. They became inspiration. One of my favorite discoveries was realizing Noet isn't entirely hypothetical. Astronomers have already discovered multiple rocky planets around red dwarfs that may be capable of supporting life. Proxima Centauri b, LHS 1140b, TRAPPIST 1e, Kepler 186f, Barnard Star b, L 9859f. We don't know yet whether these worlds truly have atmospheres, but every new discovery makes worlds like Noet feel a little less like fantasy and a little more like tomorrow's astronomy. So far, we've built a planet that can regulate its temperature. We've seen how a thick atmosphere redistributes heat, how cloud systems become a natural air conditioner, how time can be measured without a sunrise, and how infrared light gives Noet an entirely different character than Earth. Red dwarf stars aren't just long-lived, they're also incredibly violent. Their powerful stellar flares and ultraviolet radiation can strip away atmospheres and threaten the very chemistry life depends on. So how does a world like Noet survive long enough for life to begin? That's where we'll pick up next time. We'll explore how volcanic activity, atmospheric recycling, cloud cover, and ultraviolet light all work together to create not just a habitable planet, but one where life has a chance to emerge and endure. I'll see you in the next episode. In the meantime, keep creating, because every world begins with imagination.